Hi, my name is Ghulam Muhyiddin, and we will be talking today about weak heaps. So let's first start with the introduction and the history of weak heaps. So weak heap is a data structure which is defined by relaxing the requirement for a regular heap. It was first coined by Professor Ronald D. Dutton at the University of Central Florida in early 90s. There are certain rules for the weak heap for which we'll take a look at. The first one is that value in any node is at least the value of any node in its right subtree. The root node has no left subtree at all. And the last rule is nodes which have less than two children except the root node will appear on the last two levels of the tree. So let's take how a weak heap looks like. So here's a weak heap. You can see 25 is the parent node, the root, and then we have no subtree on the left side at all. And the last level has less than two nodes. Why is it even called a weak heap? What could be the reason for that? So a weak heap does not necessarily mean that it is less efficient in one way or the other. Rather, it is different from the regular heaps, and it does not require that all the bottommost nodes to be as far as possible as it is the case with the regular heaps. Also, the node values in the left subtree is unrelated to parent node. So we'll see how to merge two weak heaps together. Let's have a quick look at that. So there are certain steps for that. The first step is that root node will having the greatest value is the new root of the merged tree. Step two is that the smaller tree with smaller root node becomes the right child of the root in step one. And the last step is remaining right child of the tree with the larger root becomes the left subtree of the root of the tree in step number two. Let's have a diagrammatic representation of this. So let's say we have two weak heaps here. As you can see that this is as you can see that 36 is the root node over here for the first weak heap, and 26 is the root node for the second weak heap. And then we have subsequent nodes as well. Now, how do we merge it? So if we go back to the rule again, first thing we have to pick the largest of the root nodes here. And for that, we pick 36. So that would become the root node of the new merged heap. So it goes like this. 36 is the root node. And then the second heap became the right subtree, just like we said in the rule that smaller tree with the smaller root becomes the right child of the root chosen in the first step, and this one becomes the left subtree, just like we said that remaining right child of the tree with the larger root becomes the left subtree of the root. And also you can see that we are using breadth first search, so we will give index to all these nodes like in a breadth first pattern. Now let's look at the array representation. So we take an array of size n plus 1, where n is the number of nodes. In our example, the number of node is 8. So the size of array is going to be 8 plus 1, which is 9. We are representing the array with WH, which is weak heaps. And we have a rule here for any ith position in the weak heap, the left child is 2 times the I, where I is the index, and the right child is 2 times I plus 1. As we can go back to the slide and see, for example, 26 is index number 1, and its left child would have the index number 2 times 1, which is 2, and the right child will have index 2i plus 1, which is 2 times 1 plus 1, which is equal to 3. So it holds true for all the index values. Now, there's one more thing, a concept of reverse bit, which will be using to make sure that the swaps are easy. So besides the array, so we put all the nodes in an array according to breadth first search. So this is how our array looks like. And since it has one more space, we have an empty space here. Then we use a reverse Boolean array, which is like, it can have like values like 0. So how it works is, let's say that this is index number 1 and the value is 26. Now we will check whether the next value, 21, whether it is the right child or the left child of 26. So if we check from the graph, from the tree, you would find that it is the left child, and that's how we put 0 over here. Similarly, you will check for others as well, and eventually you will get output like this. Now let's talk about sorting. So this is our heap and we have to sort it. So right now, this is the largest node here, the largest value. So it is already sorted. But after you remove 36, it will become a regular heap. So we will have to break it down again into a weak heap. For that, we will divide the heap from here and here from 2 points. And this is how it is going to look like this. So 36 is already sorted, so that's why you do not see 36 here. But the remaining we break into different parts. And just like we saw how to merge in previous few slides, we'll try to merge it again. So if you merge the smaller two trees over here, which is 29 and this one, 21 and 15, so it would look something like this. So this is the resultant. And then we merge these two together to get a new weak heap like this. And as you can see again, now 29 has come up at the top and this is sorted. So we can push it as the second last item in the sorted array because the last item is 36. So 29 would be second last item in the sorted array. So this process keeps on going again and again until we are done with all the nodes. And as the final output, you get this. So this is your sorted array. As you can see, 36 is the largest, which was sorted like initially, and then 29, and it goes on like this. So why do we use weak heaps at all? So by using the reverse bit through Boolean array, all the swaps can be done in the array. So it makes it a bit faster. We do not need to bubble up each node every single time, as the rule in weak heap are eased compared to the normal heaps. So it is not as strict as regular heaps. The entire sorting operation can be done in place using an extra array index. That's why we are using an extra space there. And the last one is weak heap sort is slightly faster than the quick sort. That is all about weak heap. I hope you enjoyed the video. Thank you.